Welcome. Today we're going to be talking about vertical kinematic equations. What you will learn. Today we're going to talk about the vertical adjustments to kinematic equations, to our horizontal ones that will make them into vertical ones. It's a very small one. We're going to discuss the vertical acceleration there is due to gravity, whether it's slowing an object down or speeding an object up. And then we're going to solve practical problems using vertical kinematic equations. The first thing I want to talk about here is all objects will accelerate at the same rate when it talks about gravity, g. If we're talking about g, we're talking about gravity. If we're talking about gravity, we're talking about g. And what is g? G is always, here on Earth, it's always going to be 9.8 meters per second squared. That means if something's falling, we kind of went the wrong way there with that. Backtrack here a little bit. There we go. If something's falling, it's going to be increasing in speed at a rate of 9.8 meters per second squared. But if it's going up, it's going to be decreasing in speed at 9.8 meters per second squared. The thing I want to point out to you right now is the units here at the end. And the units here at the end tell us that it's meters per second squared. So this means it is indeed an acceleration. I don't want you to get caught up in this, all this up here. I used to really talk about that, and then students didn't get it because it's a lot of algebra. So now we just talk about the equation down here. What I want you to understand is that this is essentially a derivation of the same equation, one of the same equations we've been working with, except now we have yf, yi, it's still vit. Instead of being 1/2 a, it's 1/2 gt squared. So this is our vertical equation. We've made a few alterations in it, and a lot of times we will still use an a right here. And that's if we're talking about something that's accelerating for some reason other than gravity. If it's falling or if it's going up and decreasing in speed due to gravity, we're going to use g. But if we're talking about, for example, a rocket that's shooting up, a beautiful picture of a rocket, it's got this engine, well, it's not accelerating upwards at 9.8 meters. It's going to have its own acceleration. It's going to be a very large number of meters per second squared. So we would use a in those cases instead of g. So once again, we're going to use g if it's for something that's falling, or if it's for something that's decelerating because of gravity. Let's go ahead and use our first equation here, the only equation we're going to talk about today, and introduce this to some story problems. The first thing I'm going to do is go ahead and make a list. So I'm going to pause it and take a second here to make my list. See if you can get to pause it and do it too. Okay, at this point, I went ahead and made my list here. It tells us that its initial velocity of 35 meters per second. I don't know its final height, but they gave me an initial height. So a lot of times if I see something gives me an initial height, I'm going to go ahead and put yf in and put a question mark, because I don't know what it is. But the initial height was 2 meters. Gravity is negative 9.8 meters per second squared. This negative just simply means I added a direction to it. Earlier we were just talking about the magnitude. I've added the direction. The negative meaning which way does gravity act? It acts down. That's all this negative does. We weren't talking about the direction of it earlier, really. I was just giving you the magnitude. So, and then the first question gives me a time of 1 second. So, let's use our equation. Yf equals yi plus vit plus 1/2 gt squared. Well, I want to find how high is it. So that's my yf. Its initial height is 2. Its initial speed is 35 meters per second. The time is 1 second plus 1/2 negative 9.8, and then t squared is going to be 1 squared. what we've got here is that the final height ends up being 32.1 meters when I go ahead and punch all these things into a calculator. Okay, as I get ready to do my second problem, it says how long till it's at 3 meters. Well, I can use my same equation again. Because it's asking me for how long, meaning how much time until it's at 3 meters. Well, in this case, time is something I don't know. YF is going to be 3 because it's now saying how long is it till at 3 meters. Well, let's plug the information in here. I get 3 equals 2 plus 35t plus 1/2 of negative 9.8. You're going to see us, you'll start writing this too as negative 4.9t squared. Well, what this becomes then is if I subtract 3 from both sides, we get 0 equals negative 1 plus 35t plus negative 4.9t squared. I'm going to use something called Wolfram Alpha to solve this. This is a website. It solves quadratic equations for you. I would heavily advise you to try using that. I'm going to see if I can't get it on here for you, but I'm going to switch over and pause and find that. Okay, what I've pulled up here now is Wolfram Alpha. Your math won't be happy, but in reality here, process. What I've done here now is I've punched in the equation plus 35t minus 4.9 squared. What I'm going to do now is I'm going to solve this equation, but it's punched out in the answer. This is a graph. .1147. So you have to ask yourself which one is 7.11 or the 0.028 seconds. It's only got to go 1 meter. It's already at the 2 meter mark. So what that tells me here is it's up to the 3 meter mark. That's 7.11 is. Well, that's when it goes back down. The ball's going to go up, and then it's going to come back down. So there's up at 0.2 seconds, and here's when it will be coming back down at 7.11 seconds. Alright, well, here's our next story problem we have here. It says a model rocket is launched straight upward with an initial speed of 50 meters per second. It accelerates with a constant upward acceleration of 2 meters per second squared until its engine stops in 3 seconds. This is an example where we're not going to really use G. We're still going to use our vertical kinematic equation. I'm just not going to be using G. I'm going to be using A because it gives me the acceleration that this rocket is going upwards with. I'm going to help you make your list. Its initial speed is 50 meters per second. Its acceleration is 2.0 meters per second squared. Time is 3 seconds. The rocket is launched, usually they're launched from the ground, so we can say yi equals 0. And then the only thing you have left is yf. At this point, let's go ahead and write our equation, and then I'm going to let you try to solve it. YF equals yi plus bit plus 1/2 AT squared. YI is 0. VI is 50. The time is 3 seconds. Plus 1/2 A. A is 2.0. And the time, again, is 3 seconds squared. Well, that's where I'm going to stop here. You need to solve this one on your own. We've got another problem here. I'm going to pop it up here. I'm not giving you any information. You're going to solve it a lot of the same way, except this time they're asking you, again, they're asking you for, trying to get this off there, we go, is how long. So they want to know time. So what this tells me is you're going to have to maybe pull up that Wolfram Alpha on the website. I would just Google that and you'll find it. Hey, it's been a pleasure teaching you this evening. I'll see you on the flip side.